All right, here's our bell work. All right, there's some of our answers. And yeah, this is a protractor right here. And it is important to understand why there is two sets of numbers on this thing. Because if you look at a line, I didn't draw that very well, but let's say there's a line right here. And it's supposed to be going through 40 right here. Well, there's two ways to look at this angle. There's the inside right here, or the smaller angle, which would be, of course, the smaller of the two numbers. But if you look on the outside, or the bigger angle right here, then it would be referring to this bigger number right there, which is, in this case, 140. But this will be a pattern we need to see in today's lesson, is that if you look at adding these two numbers, you get the same value each time. That's 180 degrees, and that's on purpose, because a straight line angle, if you looked at just this angle right here, it would either be 0 degrees or 180 degrees, depending on how you looked at it. But we kind of want to look at it as a full 180 degrees like this, which also will be important for us to know. So that's why on this protractor, this one's considered 35 degrees, because they've specifically marked the angle right here. I don't know if you can see that very well, but it is marked on the inside, so that'd be the smaller of the two angles, which is right between 30 and 40, so 35 degrees. All right, here's our objective. I know what angles and sides make a triangle. Really, we're just going to be looking at sides, not angles today, at least for that part of the objective. And then we should be able to name angle relationships and maybe even solve some of these values for angles. All right, so this is kind of the beginning of our geometry unit, just because we're going to be looking at shapes and stuff, mostly triangles, maybe some rectangles. But it wouldn't really matter what type of polygon we're looking at. And keep in mind, these shapes, they have to close, right? So if you said, hey, I got 3 sides on this shape, therefore it's a triangle, it's not, because it doesn't close. You got an open side right there. I mean, you could add another side to this thing, and now say it's a quadrilateral. It's got 4 sides, and that'd be fine right there. I mean, assuming I drew it better, but the way this works, no matter what type of polygon you're looking at, triangle, quadrilateral, however many sides it has, doesn't matter, is what you'll see is the corners of these labels. We call these vertexes or vertices. A vertex, a single one is a vertex, okay? These are labeled usually with capital letters, so something like this. A, B, C, D, and it doesn't really matter where you start. But what happens is it creates side lengths for us, which we need. For example, like this one right here. But it's labeled by the corners of the shape, or of the line right here. So this would be side AD, and just to indicate that it is a line, or part of a line, we put a line over that, okay? Same with like this one right here. This would be called DC, and then we put a line over it. And it is possible to write these backwards, and just so you understand, at least for us, the order will matter sometimes, right? For example, AD indicates that you would start at A and then go to D. DA would indicate that you're starting at D and then going to A. Now, for what we're looking at right here, it doesn't matter. But when we start naming angles, it will matter. It will. All right, let's talk about triangles. Well, triangles are a 3-sided shape. Of course, it needs to close. I don't know that I'm going to say that too often. We kind of just expect you guys to know that. But the labels are going to work the same way. And technically, it wouldn't matter what letters you use. Like if you want to be creative and do something awesome, you probably put these letters on it. But that's up to you, okay? Now, of course, we just seen you can label the side lengths, right? You could say, well, this side length right here is UT, and this one here would be side length UE, and then the next one ET or TE, doesn't matter, right? So we get these side lengths. But one thing we need to understand about triangles Oh, by the way, mathematics, if I haven't said this before, math people are pretty lazy about this stuff. We don't actually like to write the word triangle. So what do? We actually just write a triangle right there. So this would be triangle, I don't know, let's just put the letters randomly. There we go, okay. So this actually reads triangle UTE. That's good, that's a good one, right? So anyways, that again, this is shorthand though, right? It's mathematics, and we can write this shorthand, but it would read the same way as if you were to write with actual words, triangle UTE, all right? So some niceness in math to be able to not have to write full words out. And of course, that's because it's comprised of these corners of the triangle, okay? Now, there is something about the side lengths of triangle that we need to know for what would have been our first lesson today. And that's if you look at a triangle, right? Let's say that you had side lengths for a triangle. I don't know, something like this. So let's say that this is a side length. Doesn't matter what it is. And then this is a side length. And this is a side length right here. And we don't really need to apply numbers to them, but there's something we should notice about the two shorter side lengths, the one in green and orange. They're kind of short right there compared to the purple one, right? So you'd say, hey, look, I'm going to take this green one, and I'm just estimating, but let's say that this was the green side right here, okay? And then if I took the orange length and just if I try to connect them, you see how it's too short right here? That's a problem. That is a problem. And it actually gives us something that we need to know in the first part of this lesson. And we should be able to think about this as well. What about these two shorter sides needs to be true? Well, if you take the two and add them, they need to be bigger than the biggest side, all right? So let's look at a different one like this. Like if the green side was really big and the orange side was, I don't know, really big like this. Okay, see now I can construct a triangle from these side lengths, and that specifically has to do with the biggest side and the two shorter sides, right? The two short sides, and you could think about this too. If the two short sides were just the same as the biggest side right here, could you make a triangle out of it? Well, if you did that, here's what you'd end up with, right? You'd end up with this side and this one and this one right here, right? But the problem is, as soon as I connect the green and orange side, it's just as long as the purple one. So what would happen is you just lay them right on top of that line, and you wouldn't actually be able to make a triangle, okay? But as soon as they're longer than the longest side, the two sides together are longer than the longest one, then we can, right? If I said, okay, I could make a triangle out of this thing, and yes, I'm still just approximating. Okay, now we can get one that closes, even if I drowned that better, it would close. Okay? So that's what we have to remember when we look at three sides of a triangle. The two short sides, the two shorter of the sides, they need to add up to be more than the biggest side. They can't be equal, and they can't be less than. They cannot. So when we look at an example like this one, where it says, can you make a unique triangle? Can you make more than one triangle, or is it not possible to make a triangle? What we would say is we got two of the shorter sides. And again, this didn't show us the triangle, not that it has to, but if it did, we'd have to say we're using the letters A, B, and C, right? How do we know? Because it told us the letters right here. There's A and B, B and C, A and C. Those three letters need to be for this triangle. But we run into a problem because the two short sides, 3 and 3, if you combine them, they need to be bigger than the biggest side, right? And if I say, well, the two short sides is 3 and 3, that's 6. And if I compare it to the longest side, AC, now it's shorter. Which also means that if we were to draw this triangle maybe a little bit better, you wouldn't be able to connect the two lines right here. Something like this. And so B, like, where the heck is B, right? Because it doesn't close. So this one, as it turns out, if you see a situation like this, it just means you can't actually make a triangle. It's this one. Now, I'm actually going to make up kind of our own examples on this one. So let's look at an example up here. So let's look at 3 different side lengths. And I'm not going to put units on them because I'm too lazy to right now. But let's say that you had side lengths of, I don't know, 10, 10, and 10, like this, right? So let's say that this were the 3 side lengths of a triangle. Could you make a triangle out of this? Yeah, sure you could. Now, some people get stumped on this one because, like, well, which one's the bigger of the 3? It doesn't matter. You could say it's the first one, the second one, or the third one. It doesn't matter. But if you take the 2 other sides, even though they're equal, and add them together, it's going to be bigger than the other third side, okay? So that's kind of a unique scenario, and if you see it, it's important that you know what to do with it, okay? Or if you took 3 side lengths, well, you guys give me some numbers, 3 numbers. All right, 24. Could you make a triangle out of this?
Yes.
You sure?
Yes.
Yeah, that's good. How do we know? I mean, is it because 16 plus 24 is bigger than 12? No, it has nothing to do with that. It has everything to do with 12 plus 16, right? That would be bigger than 24. Just barely, but it's still bigger, and that's all that we really need. Well, what if we ran into this type of example? You guys want bigger numbers?
Yes.
Like 1,000? All right. Sorry, what was it?
1,632.
1,632. Let's go with another one. 2,000. Well, not quite that big. 2,000. 21. That's a good one. Okay, so let's go with this one then. Let's go with the 3, 5. Sorry, I'll do this one. Sorry. All right. If you looked at this number right here, that's 3,953. Can you make a triangle out of these 3 numbers?
Yes.
Yeah, here's the problem, and I'm glad that everyone seemed to notice this one, is if you add the 2 shorter sides, it equals the bigger side, right? And if it equals it, then yeah, this one, you cannot make a triangle. So, yeah, on these other ones, I should have put yes on those ones. So again, it can't be equal. It cannot be equal. It has to be bigger. The other 2 sides, the sum has to be bigger, okay? So what has to be true about the 2 smaller sides of a triangle compared to the third side? Yeah, the sum of the lengths of the 2 small sides, it has to be longer. It must be longer than the longest side. So naming angles on triangles or even any other type of polygon is pretty crucial, okay? Because there's a couple of ways to name these correctly. And we'll see them, well, put on the assignment. I think it did some of those incorrectly, you stinking jerks. But if you wanted to do this correctly, this is how it would work. And let's start with just triangles, because we're going to be looking mostly at triangles like this, okay? Now, some of you guys, this happens to me often, because my drawings suck, but sometimes it doesn't close. Just ignore that kind of garbage, okay? Some of you guys are like, it doesn't close, it's going to drive me nuts. Well, when you draw it, then make it close, okay? But for me, it's not closing, and I'm okay with that. So let's go and name this one. It doesn't really matter what it, like X, Y, Z. I know I make my Y's lowercase. That's on purpose, by the way. But they should all be capitalized. So naming the angles, we've already talked about naming the side lengths for any type of polygon. But naming angles, it's going to work a little bit differently, because if I wanted to look at this angle right here, now some people would say, oh, actually, let me go back just a little bit. Angles. Remember how I said that we didn't, as math people, we don't like to write the word triangle? Because like eventually you have to write it so many times. Sometimes you start losing sleep over that and you get arthritis or something. Well, it's the same thing with angles. It's a big word, and we don't like writing that word all the time, okay? So we actually use a symbol for angles, which looks kind of like this. And yes, sometimes it kind of looks like a less than symbol. Forgive us for that because, well, we're numbers people. So this is our angle symbol, and so we don't actually write the word angle, but if you see the symbol, it would read angle, right? Instead of writing the word angle. And I hope you guys find an appreciation for that kind of stuff, because it was set up many years ago by math people you could call them y's. I don't really care if you do, but in any case, this angle, the one we've marked in red. Okay, so it's say, oh, that's angle. And one of the problems is some people say, that's angle X. Okay, well, that's fine if you were looking at something strictly like this, meaning that if we just limited the lines to line segments or side lengths like this. But to be more specific, again, the way that the angle is created is really what we're looking at. And angles measure kind of this space between these two lines, okay? And that's why we use degrees on this, a degree thing. But I would say that it's inappropriate to name an angle just like this with X. What we want is you have to include 3 letters to name an angle. So you'd say, if I went counterclockwise to create this angle, then just with the points that were given, I'd have to start at this point Y, right here. Then I would go to X. See how I'm kind of forming the 2 lines that make the angle? And then from X, I would have to go to Z. So this is angle YXZ, like this. Now, it is possible you could name it angle ZXY. Again, the order, at least for now, is not important, but eventually will be, right? ZXY, to create the 2 lines that make that angle. So it's also true if I wanted to name this angle right here, it would be angle. I would say, for me, I would start at X, then Y, then Z. X, Y, Z. Or this angle, I'll put in orange. That would be angle Y, Z, X. And again, just naming these is pretty crucial because it very clearly, when we use 3 letters, it very clearly tells whoever's looking at this diagram exactly which angle we're referring to. Now, something else you should notice about this, I use different colors to indicate that we're looking at different angles. But if you look at triangles in general, what's going to happen is, if we want to indicate that they're different angle sizes, then what we would usually do is we're going to mark them in a different way. So I'd say, okay, you'll usually always see 1 mark on one of the angles because it's convenient, but it is possible that you may see angles marked with 2 marks like this. And again, we put 2 marks on this angle to indicate that it's a different size than this one. If it were the same size, then I would say, look at this angle right here. I'm going to make it the same size because I give it the same marking. Now, I don't really care what those sizes are of the angles, but another way to do this is if you mark them with, like, well, tally marks like this. So that first one, that would be like our first angle, and then this one, if it were the same, would give it 1 mark. If it were different, it's possible to give it 2 marks like this. That is also true for side lengths. We just don't have the arc for the angle marking. So you'd say, hey, I got this angle, this side length, and then this side length, and then this side length, like this. And again, the different markings indicate that they are different sizes. Does it mean one's bigger than the other? We don't know unless they give us more information. And I believe there's a way that we may see on the assignment where sometimes they'll put like a letter inside the angle. They'll say, this is angle, I don't know, T right here. And this is kind of appropriate. Again, it's not as specific as saying YXZ. And this is why this becomes important, okay? Because when we just draw triangles like we just did right there, it's like, oh, that's pretty and it's colorful and I love it so much. But if we start drawing like actual lines through some kind of intersection like this, and I said this is the intersection X, then it's like, well, which angle is angle X? Is it this one? Is it this one? Maybe it's this one. Who knows? Who knows? Without more information, we can't tell. See that? So that's why it's important to have 3 letters. And yeah, usually there'll be more letters like these, A and B. So now if I looked at this angle right here in purple, that would be angle A. There's angle AXB. And then it's more specific, and we could say, oh, I can follow A to X to B, and now I know for sure what angle AXB is. But if I said angle X, Well, that seems like something that'd be kind of mean. Something else we should understand that we're going to see today is solving equation stuff. And since we love that unit so much, we'll see it quite often actually. So with angles, last thing, hopefully. If you look at an angle like this one, let's name it. Doesn't matter what we name it. I used ABC, so DEF, right? So if we look at angle DEF, need more space there. What you'll see sometimes is an M in front of that. The M here, it stands for measure. And so this reads, again, if we read it mathematically, this would be the measure of angle DEF. So that means that we'd be actually looking to measure this thing, or find a measurement for it. So what has to be true about the measures of the angles of a triangle? Yeah, this is pretty crucial as well. Let's get into that, actually. I'm going to come back to number 6 later, okay? Yeah, here we go. All right, angles that are adjacent. Okay, so I'm looking at specific examples that are adjacent, of course. So adjacent angles, what they need to have is they need to share a vertex, which again is they're going to share a point. Okay, so we're looking at two lines that come together that create a vertex, which we kind of saw in the last couple of triangles we've done. But they also have to share, we'll put and, with both. It has to have both. It has to share also a line. Okay? Another way to say adjacent is just that they're next to each other. So if we saw a diagram, well, I'm not going to put the point there yet. If I got two lines like this, then it is possible to say that this angle, whatever it is, and this angle, they are adjacent because they share this point and this line. Okay? Or if we had more lines coming out of this, let's say we got this line right here, okay? Then I'd say the purple and the red are adjacent because they share this vertex and this line. Now for a non-example, we could look at the purple one and the green one. So, and well, I guess you could say they share the line. Maybe perhaps what I should say is instead of line, ray. That's more technical than I want to be though. You'll learn more about rays next time, but a ray has a starting point, which in this case would be the green point, and then it goes on forever like this. And then we could see that the purple and green do not share a ray. They do share a vertex though, that green point in the middle. So just remember that adjacent just means next to each other. If they're not next to each other, they're not adjacent. All right, here are some examples of what we call complementary angles. And it's talking about adjacents and non-adjacent. I think we'll talk about that as well. But there's two examples that are not complementary. What we're really trying to get you to see on these two examples is 39 and 51. If you add them together, you get a very specific number, which is pretty crucial. And we kind of saw it in bigger numbers on the protractor for the bell work today. And that's also true for 47 and 43 right there. If I add these two numbers together, it doesn't matter which set I start with, but like 39 plus 51, boom, 90 degrees. Or 47 plus 43, 90 degrees right there. See that? Now these other ones, like if you were to add these together, it's pretty close, right? You'd say 99 degrees, okay. Or like this one, that's 119 degrees, looks like. But they're not 90 degrees, that's what we really need. And so when you see complementary angles, it should be two or more angles that add up to 90 degrees. Okay, the sum, I'll put that in here, the sum is 90 degrees. Now when we say sum, does that mean it has to be only two angles? No, it could be three angles, it could be four, it could be 90 angles, who knows? But for the most part, at least for now, we're just going to be looking at two angles, but sometimes we may see three. The complementary angles should add up to 90 degrees. Why is 90 so unique? It's because it creates a new relationship for us, and we call that perpendicular, which we'll talk about more in a later time. But when you see a 90-degree angle that's formed by many angles, like we do in this first example here on the left, thank you, it's usually marked. It's usually marked with a 90-degree angle mark. So you saw on those last examples where we're using kind of an arc in between an angle to show that it's an angle, right? Well, a 90-degree angle has a special marking, and that's this little corner box like this. And some of you guys are thinking, that doesn't look like a corner box. You got to work on your drawing. I'm working on it, okay? Give me another like 50 years and I think I'll get there. So I'll give examples of the two measures of two complementary angles. Okay, these are common ones anyways. 45 degrees, and then just if you're thinking, well, if one's 45, the other one of course has to be 45. That's when we split the 90-degree angle exactly in half, right? Another common two angles that we would use is 30 degrees. And just think about this, if one's 30 degrees for complementary angles and we're only looking at two, how big would the second one have to be? Yeah, 60 degrees right here. And these are two very common combined measurements to make complementary angles. So here is another vocabulary word for us, supplementary. Supplementary. If you look at these two examples for us, here these first two, then we've got two non-examples. Again, you'll notice the same thing. Like if you took 85 degrees and 95 degrees and added them together, you would get 180 degrees. And we've seen the uniqueness of 180 degrees on the protractor example for the bell work. The same is true for 75 degrees and 105 degrees. Those added up equal 180 degrees. Okay? And then for these other examples, yeah, like 80 and 120, that's like 200 degrees. That's no good. And same with 93 and 137. And what is that? 230 degrees. Nope, those aren't going to work. They have to add up to 180 degrees, which means the sum of the angles has to equal 180 degrees. Okay? And again, we're just looking at two angles for now. However, in the future, we may see more than two angles at a time. And if they add up to 180 degrees, it is considered supplementary. Give examples of measures of two supplementary angles. Here's some common ones, two common ones, okay? That would be 90 degrees plus, well, 90 degrees, right? 90 cuts that 180 right in half. And a 90-degree angle, two angles add up to 90 degrees, that's complementary. But these two angles add up to 180, so that'd be supplementary. Another common one would be 135 degrees and 45 degrees. That adds up to 180. And so therefore it is a supplementary relationship. So supplementary angles, again, if you combine them, just like we see in this example right here, with the 85 degrees and the 95 degrees like this, what happens is they create, from this point, they create a straight line that goes through that point right there, okay? So that's 180 degrees. Therefore, it is supplementary. One way that I think about this and can memorize it is that supplementary starts with an S, and this is also considered a straight line. Supplementary angles should create a straight line when they're put together. Yeah, there's another way to say the same thing we did for adjacentness, specifically with angles. All right, here's a triangle, and what's going to happen with this triangle? You're going to see something unique that happens, which is going to lead us to that other slide. What was it, question 6? So we're not actually going to cut these out as much as you may want to, and that's more for time right now. But what I am going to do is I'm going to take these three angles, okay? So I should be able to take these angles, and they're already numbered for us, which is nice. Okay, so if you cut these angles out from this triangle, by the way, this would work for any triangle. no matter how big the angles are or small, as long as it's a triangle. This will happen every time. All right, so if I took, let me see if this will let me grab this. There we go. Here's my green angle right here. Okay, now I rotated it. That looks pretty good. And there's my orange one. And yeah, the closer we look at these, the more you're like, man, your angles suck. I tried. Well, what happens with these angles when I put them together, right? So I just kind of cut them out and then piece them together. Well, we got the green one right here, and the orange one right here, and the blue one right here. And what kind of relationship do they make?
Supplementary.
That's a straight line, so it is supplementary. Now, you could if you wanted to. I don't know a lot of people that want to. Supplementary, it's kind of a big word. These are supplementary angles. It wouldn't matter what kind of triangle you drew, this will always happen. Which leads us to that other slide. Yep, the measures of the three angles for any triangle. Any triangle, they have to add up. The sum has to add up to 180 degrees. And again, that's a supplementary relationship. Another way to say supplementary is that it's a straight line, right? Actually, straight lines like this, if it's 180 degrees right here, and let's say that it was split up into, well, not yet. So this one angle right here, it's 180 degrees. Now that's also called a straight angle. A lot of vocabulary today. That's good stuff. All right, here's another example. So we're going to show you something about this angle out here. It's not labeled for us, but perhaps it should. Okay. All right, here's our angles. I think I got those drawn okay. Let's see if I can move them. Oh, here we go. So there's angle 3 and angle 1. Okay, now I'm going to leave angle 2 where it is. And in fact, if you could kind of just put this other stuff out of your mind right here, these other two angles. If I looked at angle 2 and this purple angle, what type of relationship is that? So they are adjacent, that's true. In addition to that, they're also supplementary. Yeah, they create a straight line, okay? So what does that tell us about the purple angle and then these other two angles that we have over here, angles 1 and 3, right? Angles 1 and 3. Well, it means that, yes, if we look at angles 1 and 3, the green and the orange one right here, if you combine the orange and the green one like this, assuming I drew those better, then they would make up the purple angle. Come on, technology. There we go. See that? So, if we look at this, the purple is actually the orange and the green. Okay. These are remote interior angles. They're going to equal this one exterior angle right here that we had in purple. Okay. So if you look at a triangle, and it doesn't matter how the line extends out of the angles, like if I looked at this one, I feel like I should be able to draw these better, but I'm not. Well, then if you took angle 1, then you'd have something like this, and then angle 2 would be something like this. It would still make up this one, and we call this an exterior angle. Angles 1, 2, and 3 in this case are considered interior because they're on the inside. Interior is inside. Exterior is on the outside. And the purple angle in both cases is on the outside. But this is true in all cases for triangles. If you take the two other angles and add them together, it's always going to be this one exterior angle. Remote interior angles. There we go. All right, here's a big diagram, some good diagram. Well, and you see, there's this common vocabulary word again, vertical angles, okay? Vertical angles are not, we don't need that stuff. So it's telling us different sets of angles that are vertical, okay? Well, vertical just means, as we can see here, let's look at the first relationship. ABG, that's this angle, and then angle CBE, which is this one. See that right there? Those two purple angles. Now I have given them the same markings on purpose. Let's look at the second one. ABC, that's this big one. and then angle EBG, that's this big one. You guys see that? Now, hopefully that's enough for you to just kind of make some conclusions about vertical angles. Vertical angles, they're going to share a point, but they're going to share essentially the two lines. So, right, you'd be looking at this line right here, line AE, I would call it, and line GC. They share these two lines, but they share this point as well, okay? And they're through this point. I don't know, maybe that's too simplified. They have to be through the vertex or the intersection right here. So sometimes we'll draw like arrows to point to them like this, okay? But like I've shown with the markings, they have actually the same angle measurement every time. Vertical angles will always have the same angle measurement, no matter how steep you make the angles. So you could say, well, I've got something like this. Maybe that wasn't steep enough, but you'd have these two vertical angles. They would be the same if I drawn those more straight. And then you'd have these two angles, which are vertical as well. And so they would have the same measurement. Yeah, here's another way to say it. They correspond through the vertex. Congruent, this is a new word for us. Congruent just means they're equal or the same measurement. A linear pair, we've already talked about this. It's just we use different words for it. And that's the beauty of math. As soon as people start understanding it, then we change the words on them, and then they're like, what the crap is going on? And it makes us look smarter than we are. But a linear pair, like if we looked at this example right here, ABD and DBE. ABD, that's this one. And DBE is this one. You see that it creates a supplementary relationship, which also means that they create a straight line. And that's what linear means, it's a straight line. We'll talk about more about linearity in the later unit. But when it asks for a linear pair, it's just two angles that they just have to add up to 180 degrees, that's all. Now, I did say that we're going to do some equation stuff. Here it is. But yeah, we have to remember some of that, some of those relationships, like we was just talking about. Okay. So number 8, angle A and angle B. Again, those should be labeled like that. That's okay. Just with the information given, we can still solve this. Angle A and angle B are vertical angles. The measure of angle A equals 3x plus 2, and the measure of angle B equals 5x minus 6. What is the measure of angle A? Now, it wouldn't matter if we solve for angle B, because remember, they're vertical angles, which means they are equal, or more appropriately for this unit, congruent. So that means that if I were to write this out, I'd say, hey, the measure of angle A is equal to the measure of angle B. Well, here's what we know about angle A and B, right? Angle A is 3x plus 2. That's all we know. So I'd say, oh, angle A, instead of writing it as measure of angle A, I'd write 3x plus 2. And then that equals the measure of angle B, which is 5x minus 6. And here we have an equation to solve for x. Now, the problem did not ask us to solve for x. No problem. Once we have the value of x, we will know the measure of angle A, or at least we can solve for it. So right here, I would probably say, hey, let's subtract 3x. I'm going to expedite this process so we can get through more problems. But I'd subtract 3x to zero out this 3x right here. And also I would add 6 to both sides to zero out the negative 6 here. And this just kind of skips the step, but that's 8 now equals 5x's minus 3x's is 2x's. And then divide both sides by 2, and we get x equals 4. Now this can be problematic because for some students it's like, whoa, that was a ton of work right there. Like, I feel good inside, x is 4. The problem is, just like I said before, this did not ask us for x. Although we have to solve x to solve this problem. It wants us to find the measure of angle A. So I go back to the measure of angle A, which is 3x plus 2, right? I say, well, it was x, but now I think I know the value of x. And x should be 4. Then I just solve this, and you can just type it into the calculator. 3 times 4 is 12, plus 2, that's 14. But keep in mind, it asks for the measure of angle A. All angles should be labeled specifically for now in degrees. So it appears the measure of angle A equals 14 degrees. Now you should also ask, is there a way to check our work on this stuff? I mean, yeah, you can check all your work from the equation. But what we really need to ensure is that the measure of angle B is also 14 degrees, right? Because they're vertical. So I'd say, okay, 5 times it was 4. That would be 20 minus 6, 14 degrees. Yeah, so they are equal. It checks off. So knowing our angle relationships becomes pretty crucial, especially in problems like these ones where they do not give us the diagram. I mean, the diagram may be helpful, but we shouldn't need it. So number 9, angle C and angle D are complementary. Oh, complementary. What does that mean? It means that they need to add up to 90 degrees, right? So it says the measure of angle C equals 6x plus 10, and the measure of angle D equals 3x plus 26. Well, this also means that if you took angle C, I'll write this out. If I took angle C and added it to angle D, then I should get 90 degrees. Right? Well, what do we know about angle C? Well, angle C is 6x plus 10. And what do we know about angle D? It's 3x plus 26. So if I took those two angles and add them together, I should get 90 degrees. All right? Well, we just need to solve this equation. So the first thing I would do on this one is combine the like terms, 6x and 3x, that's 9x's. And then 10 and 26 over here, that's a positive 36. And this should equal 90 degrees. So continuing to solve for me, I would say subtract 36 from both sides. And that gives me, I wish I had more room on this, but that's 9x equals 90 minus 36, 60, 54. Let's write it over here so we have more space. 9x equals 54. And then the last thing we would do is divide both sides by 9, the coefficient of x. That tells us x equals 6. Now x isn't labeled in degrees, it's just the value of x. And also, we want to know the measure of angle C and the measure of angle D. But we didn't have that before, and we also didn't have the x value before, so now that we have it, let's go ahead and use it. Angle C, right? That was 6x plus 10. But now we know the value of x, which is 6. Or at least it should be 6. So we would solve this, and I'd say, oh, 6 times 6 is 36, plus 10. Boom, 46 degrees. That's the measure of angle C. But I also need to find the measure of angle D. So, measure of angle D. That was 3x plus 26. Try to organize your work a little bit better than I am, but the x we now know is 6. And when I solve this, that will give me the measure of angle D, which is 3 times 6 is 18, plus 26 should be 44 degrees. Okay, so we got measure of angle D and the measure of angle C. And yeah, we can check these as well, right? Because they are complementary, you can take the 46 degrees and the 44 degrees. When you add them, what should you get? 90, and it does. Now this also means you could have taken the 46 and subtracted it from 90 to get angle D. I recommend using this method though, where you just replace the x in the angle D equation and then confirm that the two add up to 90 in the end. Because if by chance angle D was like, I don't know, 45 degrees or 43 degrees, then it wouldn't, the two would not have combined to be 90 degrees. So always be checking your answers on these types. Number 10, angle F and angle E are supplementary and adjacent. Well, the adjacent thing doesn't really matter, but the supplementary stuff does, because we know supplementary is 180 degrees. And that's their sum, right? So I'm going to take angle F. Yeah, we'll next one. Angle F. And if I took angle F and added it to angle E.
Teacher.
All right, so angle F plus angle E equals 180 degrees. And angle F is 2x plus 20, right? And we know angle E is 3x plus 25. So when we add these two together, we should get 180 degrees here. So let's combine some like terms. 2x's and 3x's is 5x's. 20 and 25 is 45. This should equal the 180. Just simplifies the equation for us. Then subtract 45 from both sides. To zero that out, drop your 5x. Now equals 135. And then divide both sides by 5. So now x equals 27. Not degrees, right? It's just, and this is just the x value. So we have to go back to the two equations for angle F and E. Angle F is 2x plus 20. Now we think we know the x value, which is 27. And I just solved this. 2 times 27, 54 plus 20, 74 degrees. So that's the angle, the measure of angle F. And then I go to the measure of angle E, which was 3x plus 25. But now we think we know the value of x, which is 27. Sorry, I'm almost done. So 3 times 27, I'm going to pull my calculator out. 3 times 27 plus 25 is 106. So that's 106 degrees, which is the measure of angle E. And I should check, the last thing I should do is take 74 plus 106, and that should equal 180, which it does. Two angles of a triangle measure 38 degrees and 101 degrees. What is the measure of the third angle? So there's a couple ways to do this one. And here's what we know is all three angles would add up to 180, right? So I'd say, hey, this equals 180 right here. And the two angles that we have are 38 and 101 degrees. So you take the 38 degrees, 101 degrees, add those together. And then if you add the third angle, I'm just going to put a blank right there. Then it should equal 180, right? So this is what students usually do. And they don't have to show it this way, by the way. They say, well, 38 plus 101, that's 139. And now that plus the missing angle would be 180. So then to solve, you'd subtract 139 from both sides. And really, a lot of students just say, well, I just take 180 and subtract the sum of those two, and then I've got my blank, or the missing value right there, which appears to be 41 degrees. So the third angle here would be 41 degrees. And we could check. You could say, well, 38 plus 101, we know that's 139, plus 41, is that 180? Yeah, it is. And so now we know that third angle has to be 41. But again, a lot of students would say, well, 38 plus 101 is 139. Take 180 minus those two angles, boom, you get the 41 degrees, and that's your answer. Let's go ahead and find x on number 12. It is in two parts, but right here what we see is these two interior angles would add up to this one exterior angle. Those are two remote interior angles right there. So I'd say, okay, 25, and then we got the x plus 15, right? If I combine those two, then you would get that third angle, which is 3x minus 10. And then again, this just becomes an equation that we need to solve for x. So I'd say, let's combine our like terms first. 25 and 15, that's going to be 40. And then I'd be using principles of equality to solve this one. So I'd say x is on the left, numbers on the right. Not that you'd have to. You can put x's on the right, numbers on the left. That means I'd have to zero out that 40 by subtracting 40, but from both sides. And the 3x's on the number side. So I'd have to subtract 3x's from both sides as well. So that zeroes those out just like we want. Then I've got 1x minus 3x's, which is negative 2x's, which equals now negative 10 minus 40, which is negative 50. So dividing both sides by the coefficient of x, negative 2, will solve for x on this one. Negative 50 divided by negative 2 is 25. So that becomes a phantom 1. So x is 25, and we can check, right? This would be 25 plus 15, that's 40, plus 25 is 65. So 3 times 25 is 75 minus 10 is also 65. So these two add up to the same exact value as this green angle right here. And that's how we would solve for x. Of course, now that we have x, we could solve for these actual angle values, and that would work. But it doesn't require us to, even though we kind of did. This is 13. Now, what we notice about these two angles is that they are vertical angles, right? They're through the vertex. So this means that they are also the same. So I'd say 3x plus 45, that's my angle on the left. This would equal its vertical angle on the right there, 6x plus 18. Then I'm just solving this equation for x, which is all it really wants in 13. So I'd say x is on the left, numbers on the right. So that means I'd subtract 45 here to zero that out. But if I do it to one side, I got to do it the other side. Same with 6x. Let's subtract it out to make it a 0. But if I do it to one side, I got to do it the other side also. So that zeroes these out, and I got 3x's minus 6x's. That's negative 3x's, which now equals 18 minus 45, which I believe is negative 27. So we're going to take that negative 27, divide it by the coefficient of x, which is 3, just dividing negative 3 on both sides. So x equals negative 27 divided by negative 3 is positive 9. So that's the value I get for x. But we can check, right? Say 3 times 9, that's 27, plus 45, 72 there. And then 6 times 9, the x value, 6 times 9 is 54, plus 18 is also 72. So it checks off that x equals 9 is the actual solution to this problem. Just want to draw a linear pair. So what I would do on this one to draw a linear pair, just draw a straight line, any straight line like this one. And then I just need some kind of line to come out of it somewhere. It doesn't even matter where, like this one. I'd say, oh, there's where the vertex is. And then you'd have this red line with this purple, the red angle with the purple angle makes up this straight line or linear pair.